Welcome to our engaging journey through 17 essential Python interview questions for data science. Let's explore the powerful and fundamental data structure in Python known as dictionaries. Dictionaries in Python allow you to store and access data efficiently using unique keys instead of numerical indexes. A Python dictionary is a mutable, unordered collection that stores key value pairs for fast data retrieval and modification. It operates as a hash table, providing constant time complexity for common operations and forming the backbone of many important data structures in Python. We start by defining a dictionary named employee that contains personal and job-related information. Here, we print the employee's name and their skills, and then add a new key value pair for years of experience. This line demonstrates how to use a dictionary comprehension to create a new dictionary of squared numbers. The final output shows the results of our operations, the employee's name, their skills, and the dictionary of squared numbers. Now let's explore some of the fundamental Python libraries that every data scientist should know. Libraries like NumPy, Pandas, and scikit-learn form the backbone of data analysis, manipulation, and machine learning in Python. These libraries enable you to efficiently handle numerical computations, complex data structures, and build predictive models quickly. The Python ecosystem offers several core libraries that are critical for data science workflows. NumPy handles efficient array computations. Pandas powers flexible data manipulation. Scikit-learn provides machine learning tools, and Matplotlib as well as Seaborn are used for visualization. Let's take a look at the key imports commonly used in a data science workflow. Here we import libraries for numerical operations, data manipulation, visualization, and machine learning pre-processing. Next, we demonstrate basic NumPy array operations for multidimensional data analysis. A NumPy array is created with 2 rows and 3 columns, and its shape property reveals its structure. In this block, we create a simple Pandas data frame to demonstrate random numeric data generation with NumPy. A data frame is constructed with 2 columns, A using random normal values and B using random integers. The head method displays the first few rows of the data frame, giving a quick look at the data. Moving on, we visualize data using Matplotlib's plotting capabilities. A new figure is defined. Then a simple line plot is created using the values from the data frame, and a title is added. Finally, the plot is closed to prevent unwanted display in certain environments. Let's explore some of Python's most powerful tools for flexible function definitions, focusing on advanced function arguments. Python functions accept different types of arguments, including positional, keyword, args, and double xquargs for maximum flexibility. This function demonstrates how to combine positional arguments, default arguments, args for variable positional arguments, and whargs for keyword arguments in Python. Inside the function, each type of argument is printed to illustrate how the values are received and used. The function then returns the main data multiplied by the threshold argument, showcasing how default and positional values can interact in a calculation. Here we call the function with a mix of positional arguments, extra positional parameters, and keyword configurations to illustrate real-world usage. The output shows how each argument was received by the function and stored or used internally, including the tuple of extra parameters and the configuration dictionary for keyword arguments. Let's explore how conditional logic is implemented in Python with practical examples. Python's if statement is essential for building complex control flows and implementing business rules in data science applications. Let's walk through an example function that classifies data points based on value thresholds. The function checks if the provided value is numeric and raises an error if not, ensuring robust input validation. Depending on the value, the function assigns a category and risk score using if, elif, and else statements. Finally, the function returns a dictionary summarizing the classification outcome for the input value. Here's how you can use this function to classify a set of sample values and print their results. Now let's explore how to count capital letters in a string using Python. First, we define a function that takes a text string as input for analysis. Within the function, we initialize a counter set to 0 to keep track of capital letters found. Next, we loop over each character in the provided text string. If the character is an uppercase letter, we increment our counter by 1. Finally, the function returns the total count of capital letters found in the text. This section highlights how Python handles files using context managers, analyzes string content, and counts capital letters efficiently. This function analyzes a text file to count and report statistics about capital letters. The core logic reads the file and iterates through each character to tally the uppercase letter counts. It then summarizes results in a dictionary, returning the total, unique, and per-letter distribution of capital letters. The function handles missing files and unexpected issues using exception handling for robustness. Here's how you can use this function to analyze a real file and print the results. Let's explore Python's core data types, which form the foundation for all data processing tasks in data science applications. Understanding Python's built-in data types is essential for optimizing memory use and performance in data science workflows. Key categories include numeric types like integers and floats, sequences such as lists and tuples, text with strings, and specialized types for advanced use cases. Let's look at a function that explores various Python data types including numeric, sequence, text, and mapping types. This part defines sequence types such as lists, tuples, and ranges, showing Python's versatility in storing ordered collections. It also introduces text and binary types with strings and bytes, highlighting different ways to handle textual and binary data. To round out the fundamental types, the function covers sets to handle unique items and dictionaries for key value mappings. The next section builds a dictionary that calculates the memory size of each major data type using their sizeOf method. Finally, this code runs the function and prints out the memory usage in bytes for each data type, giving insight into their relative storage costs. Let's explore the key differences in performance and memory usage between lists and tuples in Python. Lists are mutable, meaning their contents can be changed, while tuples are immutable and offer better memory efficiency and faster iteration. Lists are mutable and flexible but use more memory, while tuples are immutable and generally more memory efficient for storing static data. Let's explore a hands-on comparison of lists and tuples in terms of memory usage and operation speed. We begin by importing the required modules, sys, timeit, and numpy, for efficient memory and performance measurements. The compare sequences function prepares test data and conducts both memory size and performance comparisons for lists and tuples. We use sys.getSizeOf to capture the memory footprint of the list and its tuple equivalent. The timeit module records how long it takes to double every element using a list and then using a tuple comprehension. Both sets of metrics, memory and performance, are grouped into a results dictionary for easy comparison. Finally, we run our comparison and print out a summary detailing the memory and performance results. In this section, we'll explore Python's Lambda functions and their role in functional programming. Lambda functions are anonymous, inline functions often used for short throwaway operations. They are frequently used in combination with higher-order functions like map, filter, and reduce to process collections efficiently. Lambda functions allow you to define anonymous one-line functions that are essential for quick data transformations and are frequently used with map, filter, and reduce in functional programming. We start by importing essential libraries like functools and pandas to enable advanced data processing pipelines. Here, we create a Pandas series object representing a sequence of numbers that will be transformed in the pipeline. Next, we chain multiple Pandas methods using Lambda functions to double each value, then square the results. After transforming the data, we filter for values greater than 50, and finally aggregate the results using sum, mean, and standard deviation. The next example demonstrates a functional programming pipeline using reduce, filter, and map to process a sequence of numbers. The pipeline first filters even numbers, applies squaring, and then collects the results into a list. Finally, we print the results of both the Pandas pipeline and the functional programming pipeline for inspection. In this section, we explore Python's list comprehensions and generator expressions, essential tools for efficient data transformation and iteration. List comprehensions create new lists in memory for fast and readable sequence processing, while generator expressions allow for memory-efficient iteration, especially useful with large datasets. We begin with the necessary imports for memory usage analysis and system functions. The compare list processing function sets up our experiment for analyzing memory and performance differences between list comprehensions and generator expressions. This helper function measures the memory taken by the list comprehension, which creates an entire list in memory. Another helper function measures memory for the generator expression, which is generally lower because it does not build the entire sequence at once. We also use the timeIt module to compare how fast each approach computes a list of squared even numbers. The timing for the generator expression is measured by converting it to a list within the Lambda for a fair comparison. Both memory and performance data are returned in a structured dictionary for easy interpretation. A similar structure is used for the performance results, organizing timings for each method. Finally, we call our comparison function and print out the results to summarize the differences. Let's explore the concept of negative indexing in Python. Negative indexing allows you to access elements from the end of a sequence, making it easy to retrieve items like the last or second to last entry. Negative indexing allows you to conveniently access elements from the end of a sequence, making code both cleaner and easier to read. The function demonstrate negative indexing showcases how negative indexing and slicing work in Python sequences. Here we initialize a sample list and build a dictionary with various negative indexing and slicing examples, allowing us to extract elements relative to the sequence's end. We demonstrate more advanced slicing, including reversing the sequence and complex slice patterns using negative indices. In the rolling window function, we use negative and flexible indexing to compute past value windows, which is vital for time series or windowed sequence analysis. Finally, we return both the dictionary of basic negative indexing examples and a practical rolling window application using these indexing techniques. Calling the function and printing its results allows us to see these negative indexing examples and rolling windows in action. This section focuses on advanced data manipulations and transforms using the Pandas library in Python, a critical skill for data science workflows. Pandas offers powerful tools for handling missing values, merging datasets, and performing complex data frame transformations, making it a cornerstone of data analysis in data science. We begin this section by importing the essential libraries Pandas and NumPy required for advanced data manipulation tasks. Two sample data frames are created, df1 with columns for ID, value, and category, and df2 containing ID and score columns. df2 is independently created, overlapping with df1 on ID, laying the groundwork for advanced merge operations. A group by operation is performed on df1 grouped by category, producing multiple aggregations including the mean, standard deviation, and count of value. A complex merge is conducted on the ID field using an outer join, and missing score values are filled with the score mean, integrating information from both df1 and df2. The rolling mean for the value column is computed with a window of size 2, showcasing the use of window functions for time series or sequential data. The advanced Pandas demo function is executed and its results for each operation are printed for examination. Let's explore how to handle and analyze missing values using Pandas, a key skill in data science tasks. Handling missing values is a crucial part of preparing data for analysis in data science. Pandas provides tools for detecting, analyzing, and dealing with missing data using various imputation and filtering strategies. Let's look at a function that performs comprehensive missing value analysis on a data frame. The function calculates missing value counts and percentages and applies several imputation strategies such as mean imputation and interpolation. It also examines missing value patterns and correlations and stores all results in a dictionary for easy access. The function includes various imputation methods: mean filling, forward and backward fill, and linear interpolation. Finally, we call the function and print each result to display the outcomes of our missing value analyses. Let's explore how to select and manipulate columns in a Pandas data frame, which is an essential task for effective data analysis. Efficiently selecting and manipulating data frame columns is a key skill for effective data analysis, and Pandas offers a variety of powerful methods for these operations. Let's examine a demonstration of efficient column selection and transformation techniques in Pandas using a sample dataset. We import the essential libraries Pandas and NumPy for our data operations. A sample employees data frame is constructed with departments, ages, salaries, and years of experience. The function prepares several column operations, starting with basic column selection to retrieve just the department and age columns. Conditional selection filters rows to display departments and salaries only for employees older than 35. Transformation is showcased by creating new derived columns, salary category using quantiles, and formatting experience as a string. A complex transformation computes a metric for salary per year of experience and flags employees above the average age. Finally, the operations function is called and the results of each manipulation are displayed. Let's explore how to add data frame columns using complex logic in Pandas efficiently. In real-world data science, new features often require conditions, multiple inputs, or custom functions, not just basic arithmetic. Now we'll explore how to efficiently add columns to data frames using complex logic and vectorized operations for high performance. We start by importing all the necessary libraries for data manipulation and computation. A sample employee data frame is created containing basic information like salary, experience, and performance. Now, we use the assign method to add new columns based on complex business logic in a vectorized way. First, we define an experience multiplier column that increases if the employee has more than 5 years of experience. Next, we calculate a bonus by multiplying the base salary with the performance score and the years of experience, all scaled appropriately. We add a department-specific allowance using NP Select with different amounts for IT, sales, marketing, and a default value. Finally, we classify each employee's performance into categories using Pandas QCut based on their score. Total compensation is calculated as the adjusted base salary plus bonus and department allowance. Calling the function produces the enhanced data frame with all the new calculated fields and prints the result. Data visualization is crucial for data science as it helps convey complex insights through clear and compelling visuals. Python offers powerful libraries like Matplotlib and Seaborn to create a wide variety of charts and plots for data exploration and presentation. Now let's explore how Matplotlib and Seaborn can be used for advanced, insightful visualizations of employee data distributions and relationships between variables. We start this section by importing Matplotlib and Seaborn, two of the most powerful Python libraries for data visualization. Here we define the Create Employee Visualizations function that produces multiple insightful plots for exploring employee data. We set a consistent Seaborn style and create a figure with subplots to organize our visualizations neatly. The first subplot displays the distribution of employee ages using a histogram with a kernel density estimate, giving insight into age spread within the company. Next, we visualize salary distributions across departments using a box plot, which highlights central tendency, variation, and outliers by each department. The third subplot is a scatter plot showing the relationship between experience and salary, with point sizes representing age and colors indicating department. The final subplot uses a violin plot to visualize the spread and distribution of employee performance scores across different departments. Finally, tight layout ensures the plots fit nicely and the function returns the complete figure object for further use or display. We generate a sample data frame with synthetic employee data and call the visualization function to produce the plots. Choosing the right integrated development environment is key to maximizing productivity in data science workflows. Some of the most widely used Python IDEs for data science include Jupyter Notebook, PyCharm, VS Code, Spider, and Atom. Jupyter Notebook is favored for its interactive notebooks, making data exploration and visualization seamless. PyCharm is a professional IDE offering advanced code editing, refactoring tools, and excellent support for large projects. VS Code is a highly customizable text editor with robust extension support for Python and data science tasks. Spider is tailored specifically for scientific computing and comes with built-in variable explorers and IPython consoles. Atom offers a lightweight, hackable environment for simple scripting and quick prototyping in Python. Let's take a look at some of the top Python IDEs that are tailored to boost productivity in data analysis and machine learning. Specialized features in these IDEs make complex data workflows more efficient and help streamline machine learning development. We define a function that compares the main features, performance, and memory usage for 3 top Python IDEs used in data science. Here we see the feature set for Jupyter Lab, which is geared toward interactive notebooks and visual data analysis. The PyCharm IDE section highlights advanced debugging, version control integration, and scientific tools, catering to large-scale projects. Visual Studio Code excels in extensibility and Jupyter integration, making it suitable for diverse development needs while being lightweight on memory. To easily visualize and compare these IDEs, we convert the data into a Pandas data frame. Finally, we display the comparison table by calling the function and printing its results. Let's conclude with additional resources for deepening your Python data science knowledge. Explore authoritative sources such as Archive and other professional guides for further learning in Python for data science. Let's wrap up our tutorial by highlighting key supplementary resources for further mastery of Python in data science. Here are 5 influential archive papers covering advanced topics in deep learning, scientific computing, best practices, and modern workflows with Python. Modern deep learning techniques applied to data science provides in-depth insights into cutting-edge deep learning methods for data science tasks. Python for Scientific Computing, Current State and Future Directions, discusses the evolving ecosystem and future trends in scientific computing with Python. Best Practices for Scientific Computing in Python outlines methodologies and standards that elevate code quality in research and data projects. Advanced Data Manipulation Techniques in Python shares expert strategies for transforming and analyzing complex datasets efficiently. Modern Python development for data scientists focuses on workflow enhancements, productivity tools, and effective code management for data science teams. Exploring these resources will deepen your expertise and keep you informed of best practices in the ever-evolving field of data science with Python.